All right, well, here we are for the second attempt at this. Oh boy, this is a little embarrassing today. I did this lecture at 9 a.m. this morning. We had a great and lovely lecture, and the things went very well. But then, to my horror, I discovered that this thing wasn't recording properly. So all is for naught. We're here for round two. I have another student in class with me this time, someone who was able to come in and wants to see me make a fool of myself. So here we are. All right, so here we are for CENG 3306, Mechanics and Materials, Summer 2, Term 2016. I am your instructor for this course. My name is Tanya Larson. Let's see a bit about my background. I did my bachelor's and master's at Texas A&M in civil engineering. I'm originally from Des Moines, Iowa. I graduated high school in May 2006, finished up my undergrad at A&M in May 2009, and then went to grad school to finish up my master's there in December 2010. Both of those were in civil engineering with an emphasis on structures. Then I went into industry, worked as a structural engineer in the offshore oil industry for 4 years. I went into teaching, and now I teach for Houston Community College and the University of Texas at Tyler Houston Engineering Center. So the format for these lectures is as you can see now, I am recording basically a video capture of my computer screen. And I'm going to write notes on slides as we go forward. Those will be the course notes. And the audio that you're hearing is coming from a headset that I am wearing, as it is customary to do with headsets. And then the students in the class, what they see is this same video feed is then fed into our output to a large television monitor, which is positioned at the front of the room. And they're able to see the course notes as well and take notes in class in a physical format. So anyway, there we are. So first of all, it is the first day of class, so I do want to spend some time going over the syllabus. And I'll be actually periodically checking during the course of this lecture to make sure this thing is recording, so I don't have that same error again. So this is my name. You can read that. The syllabus is up on Blackboard, so you can read through that. The regular recording times are 9 a.m. to 11 a.m. Room oh man, I can't talk. Room A216 at the UT Tyler Houston Engineering Center, which is at the A. Leaf Hayes campus of Houston Community College in Houston, Texas. That's not really important unless you're attending. Again, as I mentioned in emails, attendance is completely optional. Typically, I don't expect more than 2 or 3 students to show up on a typical day. That's fine. I just like having an audience if I can get one, but whatever, that's okay too. If I have to give a lecture to an empty room someday, that's okay. I'll make do. No hurt feelings. Then, let's see. So to get a hold of me, I do have a physical office here where I'll be doing office hours, except today, not today because of special circumstances. But most days I'll be doing office hours from 3 to 4 p.m. In my office here. If you want to call me, really the only time you can call me is 3 to 4 p.m. Because that office phone number, it can't really call out because of some peculiarities of the phone system. I can't accept a call in. But otherwise, the best way to get a hold of me is definitely via a email. That is my primary means of communication with the class. That email is tlarson@uttyler.edu, and I answer that pretty frequently, usually within an hour or even minutes sometimes, depending whether I'm in lecture or not. But that email goes directly to my phone, so I can usually answer those relatively quickly. Course websites, there are 2 main course websites. One is Blackboard, and that is where the syllabus will be posted and links to the course lectures will be posted. The course lectures will actually be posted up on YouTube, but links to a nice organized list of links will be posted onto Blackboard. And also you will need the Mastering Engineering site, masterengengineering.com. That is the publisher's website, and that is where we will be doing all of our homework and also our exams. So keep that in mind. You can purchase access to the site through the publisher, but you will need this course ID here, UTT CNG 3306 Summer 2016. Just copy that together and you'll get that. Okay. The description of the course from the catalog, stress and strain, uniaxially loaded members. Normal and shear stresses, torsion and flexural behavior, beam deflections, buckle and columns, pressure vessels, combined loadings, failure criteria, shear and moment diagrams, and all sorts of fun nonsense. Okay, you can read through all these learning objectives on your own time. It's all fairly straightforward. Some of the stuff you know what it is, a lot of it you don't, but you will hopefully by the end of the semester. Well, I guess we'll find out on the exams. And the prerequisite for this course is engineering statics, ENGR 2301, engineering statics. If you have not taken this class, please drop out and take it. If you have and you're having some difficulty, feel free to check out my statics videos. I have a whole lecture series also on YouTube that I created in the first summer term for a UT Tyler class on engineering statics. The full, basically an entire course's worth of lectures that you can review if you need to go over some material again. All right, the official text is the Mechanics of Materials by Hibbler, 9th edition. So Mechanics of Materials, 9th edition by Hibbler. And you do need the Mastering Engineering online account material. So you'll need to, so you'll need to purchase that. However, if you're looking to save a little coin, and everyone always is, especially during the summer, this here is what you really need for the homework. This here is a reference text. I'm not going to be assigning homework out of that book. So what that allows you to do, if you really want to save some money, if you really want the newest and greatest, you can buy the 9th edition, which I don't think that's the newest and greatest. I think there's actually a 10th edition. But anyway, the one thing you might do is because all you'll really need this book for is a reference. So if you were so inclined, you could actually get a used copy of the 8th edition for very cheap. I think you can get one for like $20 or something on Amazon, but it's up to you. So if you really want to save money, you definitely need to buy this, but you could just buy an older edition of this. You do need some textbook as a reference because the lectures are very useful, but obviously not enough to learn all the material you need. But if all you need is a reference, an old edition will usually work just fine. But don't quote me on that. When I give the say like the readings and the course numbers and things like that, the section numbers and things like that, I will give them in reference to the 9th edition. So that's what you'll need to be careful with. So this is a list of topics. You can read through that. We'll be going through there. There will be 3 exams. These are tentatively scheduled for these dates, but notice I do not have a final on there. So I've decided to throw you a bone on this summer term. We will not be having a comprehensive final. And the exam dates are the 20th, the 28th, and the 10th of August. Now, this entire course, with the exception of these exam times, is taught according to the method which is referred to as asynchronously. That's the education term. Asynchronously means that you do not have to align your schedule with the course, generally. I post lectures to the website. You can watch them at your leisure. You do need to watch them at some point to really learn the material in class, but you can watch them as your schedule permits. You can watch them at 2 in the morning if you want. You can watch them at 8. You can watch them at 11 a.m. if you want. I don't care. It's up to you. However, these 3 exam times, this is rigid. This is the one time where you need to make sure your schedule is available at this appointed hour. If your schedule does not permit this, well, let me know. I might be able to work something out, but generally there's not a whole lot I can do. For academic integrity purposes, everybody needs to take the exams at the exact same time period. The exams will consist of a special problem set on the masteringengineering.com site. The exams themselves, I'll design them to take about an hour to an hour and a half, but the exam time will run from 6 p.m. to 9 p.m. Mainly that's just to give people, not so they have tons of extra time, mainly I give that just so in case people have computer problems and things like that. If I design it to last an hour and a half, theoretically someone could get through the entire exam, have the whole thing crash on them and not being able to submit it or something, and they could do the whole thing over again and still be able to do it. But anyway, this is an online course. And so one thing I am assuming when you sign up for this course is you are expressing that you have access to a reliable computer and internet connection. If you do not have access to that reliable technology, you probably want to take this class in person during the regular semester, unfortunately. there is simply not a whole lot of greater options. This is an online class. You need access to the internet. You need reliable access to the internet. The exams will be done online. If you can't access the internet during the exam time, you're not going to be able to pass the exam. I wish I could give a bunch of special times to people at different hours to meet their schedules, but it is difficult enough to ensure academic integrity during an online course. But at the very least, I need to make sure that everyone is taking the exams at the same time. So that's the unfortunate reality of it. Homework will be assigned at a regular basis. It will be consist of problems on the Mastering Engineering site. It is due at the date and time indicated on there, and we'll go check out the Mastering Engineering site after we finish with the syllabus. Grade distribution, it's fairly simple. Homework is 25%. Each of the midterms is 25%. I may apply curves and extra credit and such at my discretion. But generally, don't worry, curves never hurt you, they only help you, so we'll see. Sometimes I use a bell curve-ish technique if I'm really feeling ambitious, but none of my curves ever hurt students, they only ever help students. Also, towards the end, what this note means is, inevitably towards the end of a semester, usually right after the final, I always get a medley of emails, usually 5 or 6, from various people saying, Professor Larson, oh my God, I bombed all the exams. Is there any sort of special extra credit assignment? Is there anything I can do? Is there any activity? And while I feel bad for people in that situation, there's really nothing I can do at that point. If a whole bunch of people ask me at once during the semester, hey, is there something we can do? Then in that case, I can sometimes help people out. But I have to be fair to everyone. If anyone gets an extra credit opportunity, everybody gets an extra credit opportunity. So, for example, in my previous iteration of this class, some students are asking an extra credit activity. So I gave them an elaborate assignment that was asking them, that I called the Great Wheel, that I asked them to, you didn't know about that, that I asked them to design the largest freestanding wheel that could be turned by human muscle power alone. And they had to do very detailed research on bearing friction and all sorts of things I'd never seen before, and it was quite fun. But anyway, so there you have it. But again, that was fair because everybody had the same opportunity. So if anybody has a chance for extra credit, everybody has. I will not give any opportunity to one student that everybody else doesn't have. Ultimately, we are fair to everyone. The exams may be tough, but they're fair. Everybody takes the same exams, everybody has the same opportunity, etc. Okay, for business purposes, a few things. Let's see, the 20th day of class equivalent. Well, we actually don't have 20, actually we have exactly 20 days of class in this semester. So actually the 20th day of class is today of the final, but for university purposes, the 20th day equivalent is July 18th. The final day to withdrawal is August 1st, so be aware. Academic misconduct. Well, the university has all sorts of policies and formal procedures on this. There's a whole procedure for judicial review if we want to go through that. The university has a governing body that does all this wonderful, horrible stuff that can be very involved. But what you need to know for this class and for all of my classes is if I catch a student cheating on a major term exam, they'll fail the class. It's that simple. I don't like dwelling on that too much, but on a major term exam, if I catch a student cheating on that or any other major term grade, they have demonstrated that they have not performed with academic integrity in the class, and the result is a failing grade. So I don't anticipate that being a problem, especially in an online class, but there you have it. Those of you who are in the UT Tyler Houston program there was a very dramatic incident in my previous semester where I caught a student cheating on the final in this class, and they were thrown out of the room during the exam. But that was in front of all their friends and students. But anyway, let's not dwell on such things. Anyway, student work, I may collect it. Mainly that would consist of collecting things from the website if I need to during the semester for ABET purposes, accreditation, etc., etc. You can read through all this. Disability services. I don't anticipate this would be a big issue for online, but you never know. I am just a poor engineer. I am not a doctor. I am not a psychologist. I don't know anything about such matters. I don't think I ever took biology past middle school, so isn't that lovely? I do not know anything about such things. Although I did take an introduction to psych course, so if that qualifies me as a psychologist, man, you got problems. But okay, we all have problems then. So no, an introductory psychology course does not qualify me to practice psychology. Again, I'm not a doctor or a psychologist. So if anyone in the class needs any special accommodations, I do encounter this from time to time, and that's fine. That's what the Disability Support Services Office is for. You bring them your documentation. Say I have so-and-so need, and they look at they have the medical people on staff, they can vet things properly, and then they send me a letter saying, okay, we've reviewed student A's documentation, they need this, give it to them. I'm like, okay. So sometimes what that means is sometimes students, for example, have maybe a visual issue, so they need to, maybe they have visual impairment, so they need to sit at the front of the classroom, or maybe they have, some people with certain learning issues have difficulty taking an exam in anything except an extremely quiet environment. So I'll have to, even the rustling of papers around in an exam room, in a big exam room, is enough to distracting enough that they can't do well in the exam. So I set them up in the really quiet room in the testing center, something like that. That's what I mean by an accommodation. So we can work with anybody, but again, I am not a doctor, I'm not a psychologist, I'm not a psychic, so don't bring me medical stuff, just take that all to that office and they can deal with that. And then send me a note saying what I need to do. We can read through all this. Emergency exits and evacuation. This is an online class, so if you are one of the handful of students attending in person, well, please be aware of this building's emergency exits. And if you are watching this in your office, bedroom, or other domicile, please be aware of where your own front door and window are. Thank you. All right. And so that's the syllabus. If you have any questions on this, please feel free to send me an email. And are we still recording? Yes, we are. Okay. So with that out of the way, I would like to show the masteringengineering.com site, bring this to everyone's attention. So let's see. Let me go there. Masteringengineering.com. Oh, I need internet. Just give me a second. Little technical difficulties, and we're still recording. That's okay. Okay. Always some growing pains the first time in a new place. Okay, come on, we'll have it quickly here, and we're good. So you log in using your username that you create. And let's see. So let's first look at the roster. Let's see, is everybody, how many do we have? We have 13 students on here. I believe we have, how many do we have in the course? 19 or 20? So there's still a few people who haven't signed up yet. Make sure you do so. This is absolutely essential to passing the class. All of the exams will be given on this site. All of the homework is due on this site. If you do not have access to the site, you will get a 0 in the class. Don't do that. That's a bad thing. Okay. Is this if I was running a radio show, this is the time I'd click the button where it goes a 0.00 Animal House quote. Anyway, okay. So I don't have all of the courses assignments on here, but you can kind of get the feel for what kind of format this is going to take. See, the first assignment, if you notice, is due tomorrow at the end of the day. It is a introductory assignment on the website itself. Then we have a homework on due Wednesday at over stress analysis design, then strain, etc. And we're just going to keep on going. This is a very intense class. I mean, in terms of what type of time commitment, the general rule for courses is 2 hours studying for every hour of lecture. We have 8 hours of lecture a week, so including the time to watch the lectures, I'm anticipating 24 to 30 hours a week of work. So if you don't have that much time available, well, you might want to reconsider the class. This is a very time-intensive class. And I know many of you are working, a lot of you are doing internships and things like that, so I do feel for you, I do have sympathy for you, but unfortunately, it's just the reality of it. I have a certain amount of material I gotta teach you, and I need to certify at the end of the semester. When I am giving you a grade, I'm certifying that you know this stuff, that I've taught you, and that you have demonstrated competency in all the materials of this course. And so that's my standard I need to use when grading your work. Okay, so with that, I think we can actually get started on some course notes for today. So there we have it. Any questions? Okay. If you have any questions on the syllabus, please send me an email and we'll answer it as best we can. All right. So each day I'm going to do, the core of my lecture is going to consist of some board notes that I worked through on some slides. I'm sitting here with a headset and a stylus and tablet, and I'm just writing as I go. So just give me an idea, a visual idea of what's happening in the classroom as we go. Oh, nope. 5. And let me try that. I want to make sure this thing's still recording. So it's earlier, even though I used the same equipment the whole first semester, so I'm not sure what happened. But let me make sure we're still rolling. And we are. Okay. Let's do this again, and hopefully we won't run into trouble next time. All right, so in the first part of the lecture, what I want to do is I want to have a few learning objectives. 1, explain the use of a general analysis approach. Explain the civil/mechanical engineering role. And 3, determine internal forces in structural members. So we're going to review all of these things. Okay. And how I would encourage you to study for this class is, these are lectures. I mean, when I put this together, these are lectures. These are not, I'm not going to divide these up into short YouTube videos and put them together by subject. No, these are full lectures. These are meant to be watched in their entirety. So treat them like you would any other in-class lecture. Watch them, take notes on them as you go. If there's something you didn't, see, if you didn't understand, stop, rewind, go back, and play it again until you understand as much as I'm explaining. But take notes in your own notebook as you go. Do not just rely on the PowerPoints or the video itself. I really encourage you to take notes because that's probably what's going to help you the most in learning this material. Treat this exactly as you would a in-person lecture, and you'll do well. Don't, and well, we'll see. Okay, so the general analysis approach. General analysis approach. Well, let's see. Well, in general, when we work on analysis, well, first of all, I should define what analysis is and what separates it from design. Analysis versus design, you can sort of, we could talk at great length about it, but essentially what analysis means is, say you have a structure and you have a known set of loads or a set of loads, and you simply want to see whether this passes certain criteria. Design, however, is where you sort of are starting with a blank sheet. You're saying, I need to actually design an object, create it from nothing, and I need to figure out my design in order to do that. So that is sort of the basic difference between analysis and design. So you start with your external load. And then from this, you get your internal forces. Internal member forces, like shear, moment, and axial force. Now, to do this, to get this, this is done using statics. You learned, or at least you hopefully learned, how to do this in engineering statics. Did you learn this in statics? Good, because I taught it to you. You better know. Okay. Okay, so yes, you learn how to do this in statics. Now, from this, what we'll learn in this class is we'll take these internal loads and we'll apply them to something higher. So we have two things to consider, both stress and deformation. Stress and deformation. So our internal forces will lead to both stress and deformation. And these together come together to create what we call performance criteria. These define performance. Performance. And then these also interact and sometimes interfere with each other. These often interact with each other as such. So stress, what is stress? We will actually define stress later in this very lecture, but stress essentially means the stress on an object. It means a force over area, so same units as pressure. We'll see that. Stress determines whether an object passes stress criteria. What I mean by that is if an object is going to actually, if say a beam or a column is literally going to fail spectacularly, say like a beam collapsing, literally collapsing, or a column dramatically buckling or something like that, that is a stress failure. The object itself is failing. Although I should point out that a stress failure need not involve an object completely dramatically failing. All a stress failure means is that an object, a system exceeds the allowable stress, exceeds the stress that we are allowed to apply on this. And so we call this, essentially, this is used to find material type. Material type defines this. And this is our stability criteria. Stability. Now, but that is not our only design consideration. We also have to consider deformation. Deformation is how much under load, how much a structure or an object deforms. So imagine the floor we're in. Imagine the floor we're standing on. We're on a second-story building, or we're on the second story right now of a four-story building. And if I were to, imagine if you were to walk across the floor, and as you were to walk across it, you could feel the floor bouncing underneath you. Say the floor was very, not very rigid, and you could actually feel it bouncing up and down like a trampoline as you walk across it. Now, even if, say, a preeminent expert in structural engineering, someone even with a doctoral degree and 30 years experience in structural engineering, came to you and said, I have 300 pages of calculations showing that I have done an incredibly detailed analysis of this floor system. I have done an incredibly detailed finite element model of this floor down to the last nut and bolt in the beams. And I can tell you 100% that this floor will not fail as you or 100 people walk across it. Would that matter? Would you be confident working or living in a building where the floor was bouncing like a trampoline as you walked across it? Probably not. That's a deformation criteria, that even if a structure is strong enough that it's not going to, say, collapse, it's still going to have limited, there's still, deformation is still a limit state that you need to consider. And so usually that doesn't control for a lot of applications, but for certain applications, for certain specialty applications, it does control. In civil engineering, one area where deformation is a critical design criteria, especially, is, say, that I'm aware of, say, very tall buildings. When you have, say, buildings over 1,000 feet high, or really 800,000 feet high, something like that, oftentimes that becomes the controlling criteria, to the point that they have to go to great lengths, elaborate efforts to reduce the deformation at the top. The deformation I'm talking about is the deformation caused by wind. If you have a very tall building under wind, it will actually sway back and forth. Without any dampening, without any dampening the system, some of these might sway many feet, a foot or two, sometimes even more. And so even if the building is in no danger of collapsing, you can't have your building swaying 5 feet each way because no one will be able to occupy the space at the top. People are going to get seasick at the top. So they either have to design the building stiff enough that that won't happen, or they have to add things like tuned mass dampers to actually cancel out and dampen the vibration present in the system. Or alternately, another example of this would be something like long span bridges. Vibration is a major concern there. You've probably all seen the video of the Tacoma Narrows Bridge. If you haven't, just go to YouTube and search Tacoma Narrows Bridge collapse, and you'll see what I mean. Now, and for our mechanical engineering friends, a good example I can think of for deformation controlling would be, say, turbine design. A turbine needs to exist in a housing, and you need to have in many cases, you want a very short distance between the edge of the turbine blades and the walls of the chamber. Otherwise, the whole point is to extract energy from the system, and if you're letting a great deal of your fluid pass by the turbine without passing through the blades, you're just losing energy. So you can't have a large gap between the edge of the turbine and the edge of the turbine blades and the housing. Otherwise, it's not a very good turbine. However, when you spin a turbine up, it has to expand simply by elasticity. When you spin a turbine up, it's going to stretch out. And so even if the turbine is strong enough, well, one, you definitely can't have it expand so much that it's grinding against the walls of the housing. Otherwise, it's going to destroy itself, obviously. But you can't solve the problem just by having a big gap. Otherwise, you're going to let too much material in, or too much fluid pass by. So you have to have some gap, but you want to have as narrow a gap as possible. But so deformation can actually be a critical case there, because the turbine blades will stretch as they spin up. So you cannot have too much deformation, otherwise you'll have a very poorly functioning turbine. But anyway, so let's talk about the big picture in terms of classes. I'm going to be really paranoid today, checking to make sure this thing's still recording. I'm not doing this a third time. Okay, got it. All right, so the big picture. The big picture. Sort of an education roadmap of where you've been, where you're going, etc. This is definitely taught with an emphasis on civil engineering, but you're in a civil engineering class, so that shouldn't be surprising. Okay, so ENGR, the general engineering class, 2301. This deals with, actually let me put something else in this bubble. This deals with rigid bodies. Dynamics also does. So rigid bodies are idealized objects that do not bend, they do not twist, they do not stretch, they do not compress, they do not deform in any way. They are impossible objects. No object can possibly exist like that. Every object will deform to a certain degree under any load, no matter how minute. But you know what? That's fine. For the purpose of finding internal forces, a rigid body assumption is actually perfectly acceptable in most cases. But not always. So rigid bodies. Oh, what just happened here? Get rid of that. All sorts of problems today. Okay. And then after this, we move on to CENG 3306 or MENG 3306. CENG 3306 and ME, Mechanical Engineering 3306. They're sister courses, very similar. The only difference is one is taught with a little more emphasis on mechanical engineering, the other is taught with a little more emphasis on civil engineering. So you'll see more pumps and turbines in this one. You'll see more beams and columns and structural frames in this one. But again, the principles are all the same. This deals with deformable bodies. So here, things actually deform when we apply load to them. Deformable bodies. This is closer to reality, although it's still all this stuff is still an approximation. Everything in engineering is ultimately an approximation. Engineering is ultimately about taking the complexities of the physical world and reducing them down to a series of understandable and simplified models, something that we can actually use to design and create something useful. Okay, so, and after this, up to here, the civils and mechanicals have stayed together, but after this, they need to go their separate ways. And the civils go study what this class feeds into 3325, structural analysis, 3336, 4412, and a whole bunch of others. 4412, 4115, and 4315. And also your capstones course and things like that. And it also feeds into mechanical engineering courses like 3309, 4115, and 4315, etc. So mechanical systems design, senior analysis, etc. Now, let's talk about loads. So we have different ways of classifying loads, and let's look at that. So I'm going to say, let's look at load classifications. So we're sort of studying the theory of civil and mechanical engineering right now. Load classifications and load types. So we can classify loads a couple ways. We can classify them according to different categories, including time and area. So in terms of time, loads have different properties, and they can exist in different combinations of these. So we can have things like static loads. This would be something like a building or a machine's piece of machinery's weight, something that's going to be constant. A sustained would be sort of like static, except it can change, but it only changes very rarely. So something like in a civil engineering context, a static load would be the building's weight. A sustained load would be, say, most of the things that are in a building. Like in this classroom, the tables and chairs would be a sustained load. They're generally there. I mean, you can if you look at a typical classroom, the chairs and tables might sit there for 10 years without really being moved very far. They generally only move when they need to do a deep, thorough cleaning of the carpet or something. Very constant. In theory, they can move, but they're not moved that often. Or maybe an industrial setting, maybe the static load is the building itself, and maybe the sustained load is a heavy piece of machinery on a factory floor that it gets moved in, and maybe when it wears out, they'll have to put another one in its place, but it's going to sit there for 20 years without moving, and as long as it's not generating large amounts of vibration, it would be a sustained load. We can also have impact load, which fairly obvious. There's different areas where I've seen impact loading. In the offshore oil industry and in coastal engineering, you deal a lot with wave impact load. And basically these are loads with large dynamic amplification factors. There's also another application that I've seen. This is pile driving, where you have the driving of foundation piles. You've probably seen that along the side of the road, perhaps when they're building a new bridge pier or something like that, or part of a highway, etc. What they'll do is they'll have a steel or reinforced concrete column that is designed to pierce the ground. And they'll use a large hydraulic hammer that it lifts a heavy weight to a great height, drops it down through a series of rails, and makes this earth-shattering, echoing clang as it hits the end of the pier. And that thing drives it down the pile down a tiny fraction of an inch. They raise the hammer up again, drop it, goes another quarter of an inch, raise the hammer up again, and keep going until the pile is driven all the way in. And also you have repeated load, which just means a load that is applied, or I cannot talk, which just means a load that is applied again and again, especially in regards to things like fatigue. There are certain load cases that are where you can have very light loads that, when they're applied repeatedly, can generate catastrophic failures simply because the material is wearing out, going through load cycles. This is one area this has caused a lot of problems in the past is actually airplanes, where you have fatigue loading, where a plane would go through many cycles over the years of, because every time it goes up in the air, it pressurizes the hull. It goes through pressurization and decompression, again and again and again, sometimes multiple times per day. Imagine, and they run those planes as much as they possibly can. So you're going through 4 cycles a day, 5 cycles a day, depending on how many flights they're doing, and just again and again and again, it can generate, and sometimes planes have failed because of fatigue loading. Area, we can also, so that's the time property. We also have area. We have concentrated loads, like point loads, distributed / surface. So these are going to be in units of pounds or kips or newtons. Distributed or surface loads. These are things like loads that are pounds per square foot or kips per square inch, things like that. Force over area. And body forces. These are loads like, sometimes like pressure, but most often things like gravity. The weight of an object is generated throughout that object. So if you have something that is a large mass, you need to make sure that thing is able to resist its own weight at all points. Load types. We can also, and these all apply in different classifications. So you can have a static, these are in different combinations. So you can have a static concentrated, a sustained body force, all these kind of things. They can have all the combinations. And then there are also load types. There's axial, in terms of the forces they produce on members. Axial, torsional. So axial force is along the axis of a member. Torsional is a twisting about the axis of a member. Flexural is bending of a member. Pressure, that's fairly obvious, like a pressure vessel. We'll learn a bit about those later in the semester. And shear. We're going to focus mainly on this one and this one today in terms of stresses. And you also have various combinations of these. You can get combined. And sometimes they combine in really nefarious ways, in such that the total is greater than the sum of the parts. For example, if you have a beam column, there's something known as the P delta effect. And you'll learn about this in, I believe, in a steel and concrete design class. If you have a load applied like this, say an axial load here, and a moment, well, as this is here, if we just had the P, that'd be fine. Or we just had the moment, that'd be fine. But combined, they do something very evil, in that, okay, this thing is going to want to bend like this. Now, as drawn, this P is directly along the axis of a member. It doesn't produce any moment. But the moment I bend this beam through this bending moment, it now takes on this shape. And through this P is now off-center. This P is now off-center. The axis of the member is on average over here somewhere. So this has actually caused a off-centeredness of the load, which in turn generates even more moments. So this thing is actually going to bend even further, which causes the load to be even more off-center. Now, this is not an infinite system. It doesn't just spiral off to infinity. It's a logarithmic sort of asymptote relationship. It does reach some limit, but it does. But in other words, the total stress on this member is much greater than what you would get if you just found the stress produced by the P and the stress produced by the moment and added them together. There is an interaction effect, the P delta effect. But that is beyond the scope of this course. So you don't have to worry too much about that, just giving an example. And then finally, these loads produce internal forces. Your loads will produce internal forces. And to find the internal forces, you will cut the member at a member cut. cut member. Now for 2D systems, this will give us 3 forces at the cut: your shear, your moment, and your axial force. And we're going to look at that after this. And 3D, you would actually have 6 forces at the cut. But generally in this class, we're concerned with 2D systems. There's a few exceptions, but generally we're concerned with 2D systems. Okay, so questions so far on this theory? Anything? Okay. All right, I'm going to give an example of determining internal forces. You should have learned this in statics, but if you didn't, this will be a brief review. If you need a review further, please consult my statics videos up on YouTube. Okay, so I'm going to do an example. I'm going to have a beam, a simply supported beam. Determine the internal force. So we want to determine internal forces at what we'll call point S. At point S. So you have no idea what that means yet, but I'll actually have to draw the beam that we're going to look at. So it's going to be a simply supported beam with 2 loads on it. Has a pin on this end and a roller on this end. Simply supported beams, my favorite type of beam. I just like things simple. Okay, I guess I'm just a simpleton. Okay, anyway, we have this load here, and I'll provide dimensions after I write the loads. So I'm going to have a 2 kip per foot distributed load on this end of the beam. 2 kips per foot. And then I have a 35 kip point load here. And this is at an angle of 345. It's a 3-4-5 triangle. I like 3-4-5 triangles. Then let me label some dimensions on some points, some point names. So I'm going to have point S here. This is the point that I want the internal forces at for whatever reason. And point A over here and B over here. And then dimensions. Uh, 6 feet, 3 feet, 6 feet, and 3 feet. Now the first step is to draw a free body diagram. We need to do a free body diagram to find the reactions. To find reactions, So I'm going to draw a quick free body diagram of this. I'm going to have AX, AY. I'm going to have my 2 kip per foot load here. Uh, 2 kips per foot. And my 25, oh sorry, that was a 25, not a 35 kip load. 25 kip load. And my 25 kip load here. And finally, my reaction BY. And the dimensions are the same as above. So let's just say 9 feet, and then this and this. Uh, 9 feet, 6 feet, and 3 feet. here. And the first step, again, to find the reactions. We can only do this for the purpose of reactions, so don't ever do this for any case except for finding reactions. But I can find the equivalent point load here for this. We use that to find reactions. The equivalent point load here, well, 2 times 9 is 18 kips. And it would be 4.5 feet from the left. 4.5 feet from the left. Now, I could go and work through the rest of this, but you've all taken statics. I trust that you know how to do this. If you don't, oh boy. But anyway, basically apply sum of forces x, sum of forces y, and sum of moments, and you will get that by is equal to 21.2 kips upward. Ay, or ax, is equal to 15 kips to the right. Yeah, that's fine. Ax is equal to 15 kips to the right. And ay is equal to 16.8 kips upward. And those are my reactions on this beam. 16.8 kips upward. Now, let's see. So now let's apply that. I want to apply the method of sections to find the internal forces at S. Basically what that means is I need to cut this at S, but in order to do that, I first want to be mindful of my sign convention. So I'm going to do a little note down here. Sign convention. A sign convention is a trade show and gathering of various placard and advertisement makers. No, that's what a sign. Get it? Sign convention. I'm sorry. Okay. A lot of crappy jokes in this class. Okay, so if you have positive shear, how does this look like? What if I basically want to define the sign convention for positive shear and positive moment. Oh, that's not that. Positive shear and positive moment. Well, positive shear will have an upward force on the right and a downward force on the left, and positive moment will have bending like this. Where this comes from is this simply is the kind of forces that are present in a system that is under positive bending. So if you have a beam that is bending in a positive direction, it's deforming like this. And that's the kind of moment that exists there. And this will then be the type of, well, actually the shear will may shift from positive to negative, but anyway, it just comes from it's a standard sign convention. We could absolutely define it any way we pleased, but it is standard engineering, civil and mechanical engineering convention to use this as our sign convention for shear and moment. So that's what we'll be using throughout this course. So I'm going to draw my shear and moment at the cut, assuming positive shear and moment. So we use the method of sections, taking a section at S. So we're going to cut it. What I mean by that is we're literally going to cut it right here. This is a cut point. So let's look at that. Let's see what that looks like. So I'm going to have a beam. I'm going to have one piece of the beam here and another piece of the beam here. And I'm going to have a 15 kip force here, my AX. I'm going to have my 16.8 kip here. And I'm going to have a 2 kip per foot distributed load up to S. 2 kip per foot distributed load up to S. This is S here. 2 kips per foot. And then, let's see. So this is going to be 6 feet long. And then let me show the other forces aside from the cut forces. Well, first, the distributed load continues on a little while longer over here. We still have a little bit of the distributed load to take care of. Although we're not going to need the right-hand side to find the shear and moment and axial force. 25 kip force here, and the 21.2 kip force here. If you don't know what a kip is, it's 1,000 pounds, but although I hope you know that by now. So we have VS, we have NS, and we have MS. Notice I am drawing them assuming positives. So I'm assuming positive shear, positive moment, and positive axial force. Tension is positive. And then I'll have to draw these opposite. So NS, I would have to draw this like this. MS, these will be equal. At every cut, you'll have equal and opposite forces by Newton's third law. And then I would have a downward force here of Vs, as shown. Then just some definitions. NS is the normal force. Normal force or axial force. Vs is shear force. So I'm going to write them and then define them. And MS is internal bending moment. Okay, so this is perpendicular to area. Normal force is always perpendicular to area. And this is results from push or pull. In the past, I've done a lot of tutoring of students at various levels, high school and college, and I've tutored a fair number of students in physics over the years. And I once heard something that really annoyed me. A student told me that his physics instructor, someone who I don't think should be teaching physics, said that the normal force is called the normal force because it's always there. It's typical, it's normal, it's normal, it's the normal force. I want to whack that person with a physics book. It's very wrong, or actually a math book. That is very, very wrong. Normal is a mathematical term. Just like you can have tangent to a curve or a plane, you can have normal to a curve or a plane. You've seen this hopefully before in your calculus classes. Normal means perpendicular to a plane. Thus, normal force, even in classical physics class, is the force that results in the contact of two surfaces perpendicular to the surface. And it's because of that kind of nonsense taught that sometimes I get students in my statics class that they will go and that they will say on a problem that has a couple ropes, say like a mass hanging from some ropes, and they're just hanging by a tension force, and when they're drawing the free body diagram, they'll go and write a big old normal force arrow on it. Because they're just thinking, oh, it's a normal force, it's always there, I'll put a normal force on there, it's got to be a normal force upward. That is very wrong, and they don't do well. So no, normal force is not called normal because it's always there. It's called normal because it is perpendicular to a plane. If you come and tell me that normal force is called normal because it's always there, I'm going to whack you with the Hibbler book, and the Hibbler book is very heavy. So don't tell me that. Shear force. Shear force is parallel to area. Parallel to area. There probably should be a 2 in there. And it results from segment sliding. From segment sliding. It is a force parallel to the area of the cut or tangential to the axis of a member. Result from segment sliding. And internal bending moment acts about an axis, the z-axis for strong axis bending. Acts about an axis about an axis, often the z-axis, and results from bending of a body. From bending of a body. Oh, that's not, a body is not one word, it's two words. I can't write. Of a body. And finally, now that I've defined all these things, let's actually solve for this. I'm going to solve for the internal forces using the left-hand side. So using left-hand side, this is all just static, equilibrium, just statics. You learned all this in statics. But I'll go ahead and write one example out. Sum of forces in the y direction, upward positive, is 16.8 kips minus 6 feet times 2 kips per foot. So essentially we're taking an equilibrium of just the left piece, plus Vs equals 0. And from this, we'll get that Vs is equal to negative 4.8 kips, or Vs equals 4.8 kips downward. Okay, sum of forces in the y direction, to the right positive, or sorry, sum of forces in the x direction, I did y. Well, let's see. I'm going to have 15 kips plus ns. See, we have the 15 kip force here, and ns going to the right is equal to 0. And this leads us to ns must actually be going the other way, equals 15 kips to the left. So this thing is actually in compression. We assumed it was in tension, it's actually in compression. If we solve this, we get ns equals negative 15 kips, which means it has to be going to the opposite direction we assumed. And then finally, the sum of moments. Helps if I write my sigmas right. The sum of moments about S is negative 6 feet times 16.8 kips, just doing a balance of moments, plus 3 feet times 2 kips per foot times 6 feet plus ms equals 0, and ms is equal to 64.8 kip feet counterclockwise, like so. And that's how you find internal forces in a beam using the method of sections. Questions on that? All right, with that, I'm going to terminate the first part of the lecture, and